Hi there, welcome back. So let's continue with this study, our study of Ironman. Okay, so now let's talk about hypotheses that we're going to take. Now we talked about geometry previously, but now before moving to some other stages like meshing and simulations, let's talk what hypotheses what are we doing. So first, I just want to give my kudos to, and here I have the geometry, because he did a really good job. Okay, so in the description again you have the link, but it's a really good job. And just to show you, also I'm sharing the geometry on Onshape, important here. So see how crazy is the geometry, all the components that you have. And here we have the assembly, and what I like about this one, that we have these assemblies and then we can manipulate it. So here I have been playing a little bit, so twisting the hands. So as you recall the movies, he has the hands in these positions on jabs here. We can do the same with the legs, a little bit modify something. Okay, also the geometry fantastic, but it can be defeated a little bit. So probably, I don't know what is this component, so maybe we can erase it. So later, or if you feel free, just get the geometry, start to erase some stuff. So probably we don't need that, and probably we can modify a little bit, erase this hole here, then see that inside we have some gaps, holes there. So trying to close a little bit, but in any case, it's a fantastic geometry, incredible job. Okay, so in the description you will find the link. Okay, and congrats again, Matare. I hope that's your name or pronounce it right. So let's move now about our hypothesis. So here we have the geometry. So after doing we talk also about that the technique that we're going to use is shrink wrap, because this one has too many components. It's a dirty, very complex geometry. So we create this initial mesh and we do everything on that. Okay, so that is one of the assumptions and reductions that we're doing. But what is interesting also, we have all these geometries, different the feature inside, 20 millimeters to 2 millimeters. So here we capture the mouse, and also we're capturing all the features. So we're not going to use this one. Okay, we're going to stay with the 10 millimeters one. Okay, but probably I would talk about some hypotheses using this one. Okay, so this is still a nice one. You see the main features captured there. So one thing that this geometry, so is you measure here. Let me go here. Okay, see that is about 2.2 meters. So I think it's not the actual dimension. So this needs to be scaled. So here I did some scaling and already have it. So this is a hypothesis. Let's say that is 1.9 meters. Okay. So this is everything has been scaled, but also it's important to talk about the mass that we need to that we're using. So we know that we need to generate that lift, but also for some stabilities and so on. So what is interesting here, that we have this STL and the thickness is a zero thickness. So what I did, and just to show you that after scaling, let me put a plane there and see that I added thickness. So I make another assumption, 2 millimeter thickness of the material of the armor. Who knows, might be true, might be not. So I think probably 1 millimeter now is too thin, 2 millimeters seems realistic. Some parts probably will be more thicker than that. So that being said, that I added some thickness there, and I can also measure here, I can come here, mass, and see that I have my volume. Okay, I have surface area and so on. So let me put everything in meters here. So this is the volume of the surface, the whole Ironman with thickness, okay, give or take. And let's assume that the material, now let's talk about the material. Okay, so what are we using? I'm sure that we're not using a strange material, metamaterial, or carbon nanotube, stuff like that. I think it doesn't exist, or still the normal human doesn't get, can get his or her hands on those materials. Probably to start, who knows. But let's say normal materials, okay? So we're using titanium, the density is something about 4,500 cubic meters. So as we take that material with this volume, we're going to get a weight, give or take, something about 25 kilos. Okay, just the armor. And recalling the movie, sometimes there are some weapons, some extra gadgets and whatever. So let's round off everything, 25 kilos. Okay, the armor. Now the pilot, Tony Stark, how much does he weigh? Okay, so let's say 85 kilos for this high. So in total now we're rounded for 85 plus 25, okay, 110. And then let's add 10 extra kilos for whatever. Okay, so let's make the assumption it's 120 kilos that we're going to work. Okay, so look at that. And a right and a wrong, who knows? Just comment in the description to see if you agree with me, but this is what I'm going to do. And now, if we look at the presentation, this one, so my initial study, I make this assumption, 300 kilos, that personally speaking, I think it's a better assumption. Let's say that this is an exoskeleton, whatever, actuators here and there, so it will be something heavy. But let's take this assumption, 120 kilos, and see that here, okay, this Ironman, this study is just generate enough lift for 60 kilos, so half the weight. Okay, so somehow we need to generate more lift. Okay, here we don't have wings, we don't have anything, so this is the part that as it is, it doesn't fly. Okay, then another assumption that is important that we have here, also we can compute this position in the center of mass, that is something there. So also will be for the stability. So taking this one for the flight conditions and density 1.2, but this stuff can go higher, and you recall the first movie that this icing problems and so on. So all this stuff needs to take into account. So the first study will be using this geometry, okay, that will update it. And let's make the assumption 120 kilos. That personally speaking, I think is way too conservative. And let's work also at sea level conditions, okay, and see what happens. But the study will consist is, we know already that doesn't generate enough lift, so somehow we need to add here some thrusters to generate that lift, but that one also will cause some other problems, that is stability. So it will be quite easy to do this study and say, okay, here you need to generate, I don't know, 100 Newton, whatever, and then you fly. But whatever you add here, those small rocket or thruster, are going to have an influence in stability, and then you need to add that control. So far I created, now it was very primitive, a control system. It was an on-off, okay? So if the momentum positive on here, off here, but it's not the actual one, we need to add a PID, which I'm working, shouldn't be that difficult to put it, okay? So the first part will be doing the polars, okay? So here we have a fixed velocity or different velocities, then we change the angle of attack. We have our conditions, weight, and so on. And then also we compute momentum and everything, and with that we can construct a small model, test our PID system, but also we are going to get a good idea about the aerodynamics. But so far it doesn't fly, okay? And the next step will be just moving here and putting everything in motion. Here will be more tricky, the control system, okay, because controlling the rotation and then staying hovering here, it was really tricky. But yes, these are the assumptions that I taken. Okay, so let me know if I'm wrong, right? Okay, I think there is no way to say, but if you want to contribute to this discussion, just let me know. And also, if you want to modify geometries and put in everything, you have the link in the description, so you can modify probably you want to change the R positions. So I recommend you to work everything in the mesh. Now, so there are some good utilities that can deform or do some sculpting in the mesh. So if you can help me with that, it will be nice. So I will put in the next video, just add the mesh, okay, with the scale geometry, which will be this one, okay. So scale geometries and have some meshes. So to do the polar study, I think the best way will be to create a round domain, so you can rotate it. It's easier. Instead, if I give you a rectangular one, you need to redo that mesh, okay. And I don't want to work for the moment with overset meshes. Okay, so that's all for this video. Thank you for your attention, and I hope somebody just jump in and can help me with this. Okay, bye.